All right, so today's lecture, I apologize for the number here. The number is wrong. I could really quickly fix that. A little bit of this 3.1 today. My apologies. So 3.1, the first lecture of week 3 is going to be talking about dynamic verification. Correctness, dynamic verification, they're all really big words. Colloquially, what we're about to talk about is known as testing. That means that, you write software and we're going to learn how to actually test that software, right? Now, testing is an idea that even if you don't really feel like you know how to do it, you kind of get the idea of it, right? It's writing code to check your code. And that's really what we're going to be talking about. So the reason why we're talking about this today is writing tests are critical to ensure applications work. That makes sense. If you don't have ways of testing your code, how do you know your code works, right? You might be really smart. You might think I'm a genius programmer. You might have kind of put some things into your program before and it seems to give the right output, but if you're not sure, if you don't have tests, then you're not really going to be as sure as you possibly can be. It's important that we talk about testing in terms of process and methodologies too, because approaching testing the right way will yield better results overall. So you can write bad tests and you can write good tests, and we're going to kind of chat a little bit about that as well. And we need to be able to understand the characteristics of programming languages and approaches to understand how bugs may occur and how you can prevent them. What I mean by that is that in languages like C, compared to something like JavaScript, the types of errors that you will get will be drastically different. And therefore, we need to also approach it differently. We're talking about some of these theoretical concepts at the start, and then we're going to go a little bit deeper into Jest, which is a really specific technical aspect of testing in JavaScript. So there's a little bit of academic theory, and then there's a bit of actually getting your hands dirty. And most importantly, this lecture is very critical for iteration 1, which I believe you've just had released. So it's very difficult to start iteration 1 without having watched this lecture. So if you're watching it live, great job. You put yourself in the best position. And if you're watching the recording in week 4, I wish you well with whatever you're up to. All right, so firstly, there's a really important word that we need to unpack, and that word is verification. Here's a very kind of hefty technical definition. Verification in a system lifecycle context, that's a way of saying like within the context of building big systems and how those processes go, is a set of activities that compares a product of the system lifecycle against the required characteristics for that product. That's quite a big, lengthy definition there in bold. So what we're really saying by that is it's just saying like we are trying to compare the system against how we expect the system to behave. That's what required characteristics are. So what I mean by that is, let's say you're in Sydney and the new Sydney Metro is being opened and someone wants to test the Sydney Metro. Well, what do you want to test? You think that the Metro should be able to speed up at a certain pace, brake at a certain pace. You need to be able to, if you develop something where you can check if the Metro train behaves like it should, then you've basically tried to verify the Metro train itself. So verification in a way is testing, like we think of, we understand testing. So think of verification as the word to just say like, if I've verified something, it means that I've gone through some set of tests in order to make sure this thing behaves how it should. Now, the definition we have here is that verification is checking if the system has been built correctly. And you should know whether something's built correctly. And this is true for pretty much any engineering system. It's not just a part of software, for instance. This is true for mechanical and civil. In all those fields, if you've done your job right, you should know what a correct system is. And if you know what a correct system is, you should be able to test it. And if you can test it, you're in a good spot, right? So Theoria says, so we write code to test the code, but then we need to test the code we wrote. So we write code to test the code. Now, so that's an excellent question. And honestly, that's one students don't actually ask enough, which is, okay, I get the idea of writing code to test my code, but how do I know that the code I wrote to test my code is correct? How do I verify that my tests are correct? We actually don't go into an exceptional amount of depth in this lecture, but what I would say, and this is kind of true throughout a lot of latter year courses as well, is that it's really, really important to keep your tests simple. I don't think it's something that like we do a little bit of this in 1531, but not a super duper amount. But it's all about simplicity. Like, so as a good example, in general, it's often discouraged to include loops in your tests, right? Because like think about your code when you write it. Like the more if statements you write, the more else statements you write, the more for loops, while loops you write. They're all the sources of bugs typically in your code, right? So, your test should be easy to understand because good programmers can identify bugs in really simple code quickly. Do you know what I mean? Like and I see if I can kind of do it. It's like if you have a piece of code here, and I know you've just started on 153.1 this week, but if you say something like, const no vowels equals vowels dot replace all a with, nothing, and we do that for E and I and U, right? Like let's take a really simple piece of code like this. A good programmer, even a half decent programmer, could look at that, and if a few of them look at that, you could identify that that is not going to be, full of bugs, basically, right? Whereas if someone was to come along and write like a funny for loop where they're like for const val of a e I o u, something like this, right? And then they start doing const no vowels equals, and this isn't to say that this particular piece of code is particularly difficult, right? Like it's still pretty straightforward, but it's a little harder. You've kind of introduced some areas of like things could go weird here. Have I done arrays right? Have I looped correctly? Am I like, even that, like this is a great example actually, because if you made something like this, let no vowels equals that, and then you wrote let no vowels equals this will actually have a bug in it because of scoping rules, which I'm not really going to get into. But the point is, like, simple code is easy to identify errors. So you also do never know whether your tests are going to be 100% right. And I love that someone's brought that up in terms of like that's a potential thing that you have to think about, because it's true. We'll talk about that a little bit more. I don't want to get too off track there for the moment. Poor software costs more than $500 billion per year worldwide. Yes, so different industries, there's different costs to software issues, right? So if you're working at a company like, say, a Canva or Atlassian, if you have a bug in your software, it probably is going to be pretty cheap. That's why those pieces of software are often riddled with bugs. Whereas if there's other, take a good example, might be like a car, right? Like the anti-lock brake system, ABS systems in a car. If there's something wrong with that, you have to recall the cars. You have to recall 100 million cars. Or if there's a piece of software wrong with, a cochlear implant or what are they called? The artificial hearts. Oh my God, pacemakers. Then they're very expensive. So it always costs money to fix, unverified software. And it's kind of why we do it. Like if you think about it, writing tests to verify software takes time, and if it takes time, it costs money. But we do it because the cost of having issues with your code will probably cost more than checking your code. And there's another question that sometimes comes up in terms, which is like, how much do I need to test my software? How far do I need to go? And there's no good answer for that, because it all depends on what's the cost of getting it wrong. So there's some industries where I've talked to people where they'll spend 1 hour writing code, like an implementation, and then they'll spend 20 hours writing tests for it, and then there's other industries where they might spend an hour writing code and 10 minutes writing tests for it. There's no right answer, but in general, in most places, writing tests is important because you need to verify your software in some way, shape, or form. Now, when it comes to verification, we can break it up into kind of two key areas. One is what we call static verification, and the other one's what we call dynamic verification. Now, static verification is testing code before it executes. And that's kind of a pretty simple idea. What that means is like if you write code, blah, 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 you write code, and then at some point you run node mycode.js, right? Everything you do that tests the software somehow before you actually have to go and run it on the terminal is what we call static verification. Now, you haven't learned anything about static verification yet. You're going to learn a little bit more about it soon with Yuchao, I believe. But, a really simple example of static verification that you probably do all the time without realizing is staring at your code, right? Like you will sometimes look at your code and be like, is there a problem here? And what you're doing is you're essentially trying to verify that it works through your own experience and knowledge without running it. That's a form of static verification. We're going to learn about a couple of forms in this course. One is called type safety. The other one's called linting. Both of those topics come up very, very soon. And it's all about before the code runs. But the other part, which is what today's about, is dynamic verification, which is about testing whilst we execute the code. And that's the kind of test where we basically run the code in a bunch of conditions. And that's probably what most people think about when they think about what testing is, because you could argue that there's many, many forms of testing, but when a typical undergraduate thinks about testing, they think, I need to write some code to run against my code. And that running part makes it dynamic. Sometimes we call static compile time checking. Sometimes we call dynamic runtime checking. There's a bunch of different ways that you could kind of think about these things or reason with these things as well. Now, this kind of gets us into another important theoretical point, which is called software safety. Now, when we verify code, when we write tests for code to make sure that it works, we will typically describe that process as making software safe for use. Now, safety is a funny term. It's different from making software secure. Cybersecurity and software security are big topics that you'll hear thrown around all the time, right? Like everyone's always talking about cybersecurity and cyber attacks and everything else. But when you think about like improving the security of the code you write is basically a process of protecting your code from deliberate misuse, or as is written there, misuse. It's misuse. So that means that there are people out there who are trying to intentionally break your stuff, to steal from you, to harm you, to do some kind of negative outcome on your end. And that's why we try and protect against that. But that's about like security protections. When it comes to improving software safety, that's basically a protection from accidental misuse. So it's fair to say that part of verification is also trying to remove bugs. And anytime you remove bugs, you remove any issues with accidental misuse. There's a little link down here that you can follow in your spare time, which says around 94% of spreadsheets contain errors. For any given spreadsheet formula, there's a 1% chance it contains an error, right? So if you're reducing the errors in an Excel spreadsheet, you're probably improving your software's safety. And software becomes unsafe when its design or implementation allow for unexpected or unintended behaviors, particularly during runtime. So like, for example, with that, the obvious ones are like reading uninitialized memory or writing outside of array bounds. So if you can write outside of memory or you can write outside of array bounds, and that isn't necessarily a security issue with your code, but it could cause a bug, for instance. Amin says, wouldn't writing outside array bounds in JavaScript not be much of a problem because it's a language that manages its own memory compared to C? Correct. Yes, exactly. So I mentioned this at the start, that different languages have different sensitivities. So for instance, with JavaScript, we don't need to spend much time doing anything when it comes to verification around code to make software safe in terms of memory. So a lot of that, for example, is much more specific to C, which a lot of you have experience in, which is why we have that example there. Speaking of C versus JavaScript, we're going to dig into that example a little bit more. C is not considered a memory safe language. What that means, and now it starts to click a little bit, it's like, what does memory safe mean? It means that on the topic of memory, does it prevent it from accidental misuse? And C is not memory safe. It doesn't protect it from accidental misuse. However, JavaScript is. You can't do an out of bounds error in JavaScript. You can't do uninitialized memory in JavaScript. Therefore, JavaScript, like many other languages, is what we would consider to be memory safe because of what JavaScript prevents it. Now, JavaScript does this dynamically at runtime. That means that whilst the code is running, JavaScript will be ensuring the safety of the code that you wrote by checking kind of constantly, hey, can they do this? Hey, can they do that? Hey, can they do this? C, there's no bounds checking at all. So therefore, it is not memory safe. And that's because C prioritizes performance over memory safety. And this is a general philosophy that you will see throughout programming, which is every time that you do something that improves the experience, not every time, it's a bit dramatic. Most of the time you do something that improves the experience, it will come at some cost. So JavaScript has a lot more baked in safety, just like Java, just like those other languages. However, that comes at the cost of performance because JavaScript has to do a lot more, whereas C's like, yeah, I'm just going to trust that you do it right. If you do it wrong, you'll get punished. But if you do it right, I'll be really, really quick. That's kind of the trade-off that happens there. Now, we're not going to talk about static verification today at all. This is just kind of a throwaway slide. But static verification is a bit of an underrated topic because when we often talk about testing, we often talk about it in the context of dynamic testing, writing code to test your code. Whereas static verification is super, super cool. It's often considered by people probably to be more reliable. But it has its limitations as well. So what I'd say, and this is just kind of a heads up for the comparison that you'll experience later, static verification, like if I could only statically verify my code or dynamically verify my code, I would probably always do it statically personally in all of the projects I tend to deal with. There's some projects you can't do that in, right? But a lot of software projects you can. However, static verification has limits. Not everything can be verified statically, and that's really, really important as well. So there are limits to that too. Now, moving on, dynamic verification, the real meat and guts of things today. So dynamic verification is the verification that's performed during the execution of software. Code has to run. This typically falls into one or two categories, which is testing in the small and testing in the large. Now, there'll be tons of different ways that you'll ever see this described throughout your degree. You'll hear like unit testing and this and that. We're going to talk about a few. But in general, you can break most software up into like, it's either trying to test a component or it's trying to test the big thing. Now, if I go back to the metro train example, you can either be like, okay, I got to test that when I move the lever up that the train speeds up, and I got to test that when I shut the door that it fully clicks and it can't be open. That's what you consider testing in the small. You're testing components of the bigger picture, whereas testing in the large will generally be, oh, I actually have to go and check out the whole thing. Does the whole train move correctly? So it's the pieces coming together. And there's not really a better or worse form of that, right? Because testing in the large gets you closer to the experience someone wants in the end, but it's not very good when things go wrong. For instance, if if all your testing is, does the train brake on time, and it doesn't, well, you don't really know where to look because you aren't testing the underlying components. So that's a really important difference as well. Now, this little quote at the bottom here, I think is a really important one not to gloss over, which is that testing shows the presence, not the absence of bugs. And it's just, practically this will have very little impact on you because, a lot of what most of you will end up doing won't be testing that extensively all the time. But the reason it's so darn important is because you can write 1 million tests and all it does is reduce the amount of bugs that exists, right? So, but never in full. So for instance, this quote here, not the absence of bugs. When you test stuff, you are trying to find bugs. You can find more and more bugs, but you'll never be sure that you found all the bugs. Someone also made a great comment earlier about code. I can't remember the exact quote, but every line of code you don't write is bug-free, is a great saying. And every line of code you do write, you can test to your heart's content to try and find bugs in it, but it'll never be guaranteed to be bug-free. Now, the reason dynamic verification exists and static testing has its limits is because real-world things happen that you can't predict at what we would call static time or compile time. What I mean by that is you can write code, and maybe that code makes a network request or it takes an input from a user or it reads from a hard drive. You can't be sure how those things are going to go until they actually happen, in reality. Because if you're making a request to a website to get some data, there's nothing you can do before running your code that will guarantee how the code will, that it'll work until it actually tries to go make that network request. And that's why we need dynamic verification, because most code is messy. Most code deals with the real world in some kind of way. Got a student saying, therefore I should write everything in one line to have as much bug freeness as possible. Yeah, probably. But that's not really possible most of the time. Okay, so dynamic testing then, you have to imagine it as it's about making your program more robust in the face of real and inevitable things that will go wrong whilst the program is running. That's the main thing. And the other part of testing that we don't talk about, because you kind of break testing up into two chunks, right? The first one, which is what I've talked about and what a lot of people talk about, is it helps reduce bugs in your code. Cool. Yeah, that makes sense. I'm sure we're 30 minutes in and most of you don't. No surprises there, I guess you'd say. But the second part is that it helps you identify regressions. Now, regressions are a funny concept, I think, if you're early on in your studies because you haven't worked in very, very large systems. But what often happens is you'll write some code, and then maybe a year later, 2 years later, 3 years later, you or someone else will come and modify that code for some other purpose. You might say, for instance, need it to behave slightly differently. That happens all the time. You might need a slightly different layout. You might need to have it take into account a new thing. Good example might be, Australia recently changed their tax brackets. So there's going to be code out there and tons of websites and apps that had the old tax brackets, and now there's new tax brackets for income. So they have to go and change that. But the thing is, every time you change code, you risk the introduction of bugs. So by having tests associated with code that we write, it actually gives us more confidence in being able to change our code because we know we can change the code. And if it breaks the tests, it's like a stopgap to make sure we didn't screw something up. It's actually really, really important for refactoring, because if you write code and then you think your code's messy and you want to rewrite it, if you've written it once, got tests for it, and you know it works, and then you rewrite your code for the same behavior and the tests still pass, you know that you haven't broken something as part of the refactoring. Whereas if the tests do break, you're like, wow, I actually broke something there. So that's really important as well. Now, this testing and the large stuff I mentioned, that was dynamic verification. Testing in the small is small types of testing. We are typically testing a function is the most common way, or a couple of functions. Another way you'll hear this referred to is unit testing. Unit testing kind of means what it implies, which is like you're testing, a unit means a single thing. Atomic testing, that's not what anyone calls it, but that name would make sense too. Unit testing, small testing, typically functions, right? There might be some slight variations of that definition, but usually it means someone's written a function that's being tested. These tests can either be black box or white box tests. We also talk about this a little bit later, but the quick summary of it for now is that white box testing is where the people who are testing your code know how the function works. Whereas black box testers, they can test your function, but all they know is what gets put in and that they can expect an output from it. And they're two different types of testing that have pros and cons. If we compare the small testing to the large testing is less concerned with making sure every single little part of your code is working and more that the big picture is working. And different people in different companies, different institutions will have different definitions of what that entails. So for instance, I've got a few here which says that we could write module tests, integration tests, system tests. Now again, kind of depends, because like module tests, someone might define as like, we're going to test series of functions together. And then integration tests might be like taking those modules, which are series of functions, and testing those together. And then system tests might be like testing the whole system. So like a system test on a website would be writing some code that goes and tries to log in a user and create a quiz and play that quiz. Like really high level. It's nearly trying to emulate people. Or, the end user, maybe that's a digital user or something, but end people. And then as you go further towards the small, they just get smaller and smaller. So the main thing I want to, point out to people is you might see something like in textbooks, there being like these, like, here are the 4 types of testing or something. But my experience and the experience of others I've talked to is just, it's never quite that black and white. It's really simple. Large, complicated pieces of code will probably have many different layers of what people refer to as tests. Maybe there'll be like 5 senses of abstraction. Small pieces of code, there might be like a couple. But the point is that there are layers from small to large, where small is typically functions and large is typically emulating a user. That's the main stuff there. Now, code time, because code's lots of fun. We're going to try and do some what I call naive testing. And here's the question. If I left you alone right now, how would you check if this function works correctly? You've got a function called getEven. It takes in nums. Nums is implied to be an array. It creates a new array called evens. It loops through every num. If each number is even, because you divide by 2 and see if there's no remainder, then we push that number to the evens array, and then we return evens. Now, what would you do if I asked you to test that, right? Well, you would probably go and try and write something like this. So if we pull up this code, for instance, it's still in the old one. Where is it? Even testing 1. Yep, so if I said, yep, there's some code, let's just first go and run it, make sure it works. Node num testing, in the right folder. Even testing, sorry. Even testing 1 does like that. If I go console log hello, not hello, sorry, yeah, just make sure this works. Easy. Yep, hello works there. And then if I was to go and grab this code, for instance, here, paste it. It's not pasting. Come on, friends. Oop, triple paste. No idea why. So there's our code there. And then if I go run that, what I can see is that the result is 2, 4, and 6, and 7. So I've kind of tested that in a way. I've kind of verified that it works. Verified. This is a good example of like, as you write tests, you can't prove that the code works, but you've demonstrated that you've taken steps to reduce the theoretical chance of bugs. Because there's lots of different things I could put here. Lots of different numbers, you know? And I'll never be 100% sure, but it helps me be sure. And I can see, okay, for 1, 2, 3, I get a 2. For 4, 5, 6, I get a 4 and 6. And for 7, I get nothing. It looks pretty good. Now, that's all sweet and dandy. However, what are some problems with that? YouTube friends, what are some issues? I'm waiting. Quite a delay on the stream, I think. Negative numbers. Someone says negative numbers. That's true. We didn't test negative numbers. Not enough repetition of tests. Have not tested negatives or a way to break the code. Nums being empty. You haven't tested how it reacts to non-number data types. Wow. So everyone has actually expressed a huge quantity of amazing answers. There's actually so many I can't even go through them. So the main common theme is people have been like, you didn't test X, Y, Z. And that's great. That's the essence of testing, is figuring out what to test and making sure that you test bunches of things, right? Negative numbers, empty lists, giant lists, big numbers. And someone's also saying, I'm guessing how well covered it is. Yep, that's great. We're going to talk about that in future weeks as well. I haven't tested how it reacts to non-numbers. Yep, all of this stuff is very, very good. But there's this one person at the end with no specific name who says you need to look at it yourself and think properly to see if it is correct. So everyone's right there, but that's the one I really wanted to nail into, which is that it relies on my in-the-moment human judgment. And if I run it again to check it again, I'm constantly having to do that checking myself. So the next thing you might do if you were writing tests is write something like this. Basically try and like quote unquote automate it a little bit. My word, it just really doesn't like... There we go. I have no idea why it does that, but that's okay. So if I go and change my test, basically the same code here now, right? It's just that, what's wrong? Why is it sad? See, look, this is me right now doing static verification, trying to figure out why the bloody... There it is. That's what I was looking for. See, that was just me statically verifying code. That's how simple it is, right? So now I go and run this, and what I see is it says doesn't work 1, doesn't work 2, doesn't work 3. That's odd, because that should work. Probably not really comparing things correctly there. Yeah, it's very difficult sometimes in JavaScript and languages too. This is a very kind of loose piece of code, but you really got to be careful when you can. It doesn't need to be literally equal to. Should work fine. I don't think that'll matter because that's like it's like softer without it. But usually what's happening here is like it might not be literally the same list or something like this, right? And this code wasn't really meant to be run. It's mostly just trying to say like. The point here is that you are now doing something where it is checking if it's correct and then it is simply telling you if it's wrong, you know? So if each of these is correct in some way, then you'll be in a better spot to tell because it should just print nothing. And if it prints text, then you know you've kind of screwed it up. So it's automated. So back to that bureaucratic participation mandate user, that's the point. You need to look at it yourself and think properly to see if it's correct. I don't need to do that anymore because it will be telling me. Let me just, yeah, so this person said you're not able to directly compare an array. You can't do that. You're going to have to compare it another way. We actually go through an example of that. A few people have some ideas. So let me just quickly look. It's kind of difficult to compare two arrays. in JavaScript, it kind of depends on the language. Some languages will make life really, really easy for you. Sometimes languages like JavaScript, they'll come out with new and new features. We kind of talk about this sometimes in previous terms where like I'm trying to think, you guys haven't learned about JSON yet because I guess we're going to do that next. But yeah, like one really simple hack around this if you wanted to is like you can kind of just compare the length of them or something, but that doesn't really work. When we do jest, which is the next topic, I'm going to show you how to compare arrays really easily. This doesn't work because the definition of this in JavaScript is it's trying to check if the objects are the same. It doesn't actually automatically check if the items are in it. What I mean by that is like, if you hold up two blue shirts in front of you, are they the same shirt? Literally no, but they just happen to be the same color, you know? And yes, there's lots of ways we can fix this. It's not the point. We weren't even meant to run this. We were just kind of meant to show you that, hey, instead of having something like this, you can turn it into this, and then it's automatically going to tell you if something's wrong. However, the problem with all of this is it's not really testing. Printing errors or visually inspecting output is a method of what I generally refer to as debugging. Debugging and testing are ways to figure out what is wrong with your code, right? However, debugging is not something that scales well. So what I've got here is saying you can't really call something a testing method if it doesn't scale well to a system. If it's code you write that checks if something's working or is just trying to poke it and understand it, that's just you debugging code. Testing is a scaled approach, and that's the main difference with debugging. Now, before we go learn about testing in more detail and how to do it properly, because this was just the spirit of testing, I want to quickly talk about black box testing. So black box testing is a notion of abstraction that essentially says when we test something, we don't need to understand how it works. Now, this is a very difficult concept to grasp, even though it's a simple concept, if that makes sense. You know, like you've probably come across many of these in your life where like it's hard to make sense of for a lot of people until it makes sense. Then it's like, oh, that's kind of totally obvious. So some of you might find this a little bit odd at the start. The way I often like to explain it is like, if I said to you, you know, let's say you and I are going to go pick up a car, secondhand car. We're going to, Condell Park in Sydney, and we're going to go and pick it up. Well, you're obviously going to say we should quickly test the car that it works first, right? Now, you might not know anything about cars, and I might not either. So what do? We go to the car. It's a Hyundai i30, some random car. I don't know much about cars. You hop in it, you turn the key, you ignition on, you put it into drive, you drive it around a bit, you turn the wheel, you accelerate and you brake and you pull the handbrake up. You don't really know how that car works, and you're not really testing that the car like actually does all the right things under the hood. What you're testing is that like you gave an input which was steer left and the car steered left. You don't really know how it did that. If I asked you to explain that to me, most of you couldn't, right? If I asked you how the accelerator works and the engines work, you'd be like, I don't know either. But you're like accelerating down, car goes forward. That's the function. The input's the accelerator, the output's the car going forward. The in-between's magic. Now, when it comes to a lot of testing code, we actually employ the exact same concept and principle, which is that we look at a code in terms of it's a function that does something and there's an output, and we don't really care about how it works in the middle. Now, the reason this is hard, I think, for a lot of people to grasp initially is because you often are writing the code right now that you're testing. So you know how it works, so it's hard to kind of separate yourself out from that because you just know how it works. So when we go, oh, let's test your code, you can't stop thinking about, it's like nearly asking the person who built the car to test the car. They know how it works, so they can't think of it in such abstract terms, right? But when we look at software, we often want to test like that, and we call this type of testing black box testing. Now, why would we ever do that if we understand how cars work or if we understand how code works? Well, even if you understand it, it's important because what you're doing is you're decoupling the implementation from the testing. You're giving the person who basically, builds the thing some freedom to not be constrained by your understanding. i.e., if you write some tests that don't need to know how the car works under the hood or the code works under the hood, the person who's writing the code can go change it without your stuff breaking, and that's a good thing. Another example of that might be like, let's say that you're giving someone some ingredients and they're going to go make a cake and bring you back a cake. You can test and say, if I give them this X, Y, Z, they'll come back with this food. If I give them A, B, C, they'll come back with that food. That's a form of black box testing. However, white box testing would be you going deeper and actually being like, I'm gonna give them this food, and then I'm gonna check if they get the pan out, and then I'm gonna check if they put the oven on at the right temperature, and then I'm gonna check that they put the food in, and they followed this procedure. Now, the good thing about that type of testing, that white box testing, is that if you have access to all of those details, like the cook and all, like exactly what they're doing, yeah, sure, you can finitely improve your confidence in that they're doing it right. Because sometimes things, and this is important, sometimes things can go right for the wrong reasons, and that's bad. What I mean by that is sometimes the car that you test might drive fine, even though it's overheating, because that has yet to affect it. So when we go into the detail white box testing and we actually make sure all the little components are working, we're even more sure that it works. However, our tests now rely on understanding how it works. And that's not, so someone says white box testing sounds like micromanagement. Yes. And what do we know about micromanagement? That it generally improves the outcome but doesn't scale, would be a really simple way of explaining it. So someone else has said, can't know what to exactly test though unless you know what it does and what might go wrong. Correct, yeah. So typically, and I'm really dragging this one on, typically white box testing is reserved for the people who wrote the code, and it's generally reserved for unit testing or testing in the small. So if you write a small function, you might white box test it because you understand it and it's quite small. Every other type of testing is generally black box testing, and even a bunch of unit testing is often still black box testing. And in this course, all the testing you do is black box testing because that's what most of testing is. So we're trying to really convey that point. Now, what I mean, and if you're still struggling to understand me here a bit, let's look at a couple of functions. We've got a function here called remove vowels and factorial. I'm going to go and open them up. Now, when it comes to these two pieces of code, if I say to a student right now, go write me tests for the code. The first one returns a new string with the vowels removed. The second one calculates the factorial of a number, right? Write tests for it. Now, I'm not saying you specifically, but a lot of people, their brain will freeze up and say, I don't know how to write tests for it because it's not finished yet, or I don't know how it works. And that's the really interesting conceptual gap to bridge, because you don't know how it's implemented, but you understand what it does. Because we have to unpack that phrase, how does it work? It's like, well, I know how it behaves, but I don't know how it gets to that behavior. I could explain it a bunch of different ways. So what I mean by that is, like, I know that remove vowels takes in a string, and I know that it, returns it with the string removed. So I know that if I was to say, if remove vowels takes the string cat, if it does not equal, what would that look like without the vowels? CT, console.log error 1, right? And then I could write another one. If remove vowels on dog does not equal DG, then console log error 2, right? And what I'm doing here is I am black box testing, because as LL has said in the chat, I just want the result. I don't care how you get there. Here's the input, give me the output. I don't really care about the details in between. And the cool thing about black box testing, which is really critical to your first iteration, is that the functions don't need to be finished yet. You need to know what the function takes in and what it gives out, right? Everyone has to agree on that first. But once that's agreed upon, you don't really need it to be done. I can go and write these tests. And yeah, when I run this code now, blackbox.js, when I run that, it will give me errors. The way I describe this is that the code runs perfectly fine, but the tests fail. And that's okay, because then what happens is that a developer comes along later, and a developer goes, well, okay, I'm going to say new string equals string. And then I'm going to, say for const vowels of, I'll do of A, I, O, U, like this. And then I'm going to go, and I might make another test here just quickly, just to really, let's go Google, which will give me like Jijil. And I do that, and I say, well, for each of that, I'm going to say new string equals the current string, but I'm going to replace the val with nothing. So then I go, sweet, okay, cool. But now I run that code, and it says val's not defined. What is it? Val, that's what I want. Cool, and I still get error 1, 2, 3. And I'm like, okay, well, what's wrong there? Well, I didn't return anything. Silly, silly, silly. There we go. New string, run it again. Error 2. I'm still getting an error 2. And what's happening here, I mean, I know this because I've done this example a couple of times. What's happening here is we're only removing one val. And I could see that just by debugging my code right now a little bit, by printing out new string before I return it, seeing what my code does, and I can see the extra O's there. And that's because in JavaScript, replace will only replace the first instance by default, and I need to use replace all if I'm going to replace all of them. And now I run my code and I don't get any errors, and therefore my tests have worked. And this is like a pretty basic conceptual workflow around, like, you have to agree on what certain functions or systems input and output. Someone can go and write tests for them independently of someone implementing it. Now, in reality, people might do these two things concurrently. A lot of companies will end up writing their tests after their implementation just because everyone's under pressure in the real world a lot of the time. However, as part of trying to get the practice right, we want to teach you the right way to do it, which is you write tests and then you write the implementation. And, you know, it's not only it's a good thing to do in terms of principles, but it's actually really nice to write code once you have tests for it. Like, if you sit down and you write tests like these ones, and then you do what I just did, it's really comforting when there's no errors, because you're like, I know my code works, right? There's none of that existential angst that comes from finishing writing code and being like, I hope it works. You know, it would really suck if I've got something wrong. So that's a pretty great aspect of things. Yep, that's kind of just what I talked about there. Sweet. Now, I think we've conveyed all the points. Personally, if you do have any, questions, then feel free to throw them my way. But the next thing to get into is about how do we actually test code. So to test code at scale, we need a real testing framework. And a framework is basically a system that is designed specifically for testing. Now, Jest is a framework used in JavaScript, both with Node.js and JavaScript on the front end. And it's installed with NPM, which Yuchao's already talked about. Now, if I just quickly Google NPM JS Jest, I want to give you a sense of the scale of this particular testing framework. It has 20 million downloads a week. I always love to do this. 20 million divided by 7 days, divided by 24 hours, divided by 60 minutes, divided by 60 seconds. 33 downloads a second. Now, I want to be clear. This isn't 33 new pieces of software. This is 33 developers a second in the world, or systems that are downloading it to run it. So a good example is a company like Canva. If it's got 5,000 employees, all of those employees might, once a week or once a month get a new version of Jest as it comes out. So, across that company of 5,000 people making one app, that might be like 5,000 a month at Canva, download it, for instance. Or, for instance, as that system is released every evening, and we talk about these concepts later on in the course. I don't know if Yuchao or I does it, but someone does. It's like, these systems, like every time Canva releases a new update, it probably goes and gets a fresh library as well. So there's a lot of downloads that happen here, but it's a significantly popular library, and it's popular for a reason. It's pretty easy to use. It looks like this. And the way it works is that it has a little structure where you essentially say, yep, I'm going to give you like a high level idea, and then you can write a test like this. So this is the test line. This is the equivalent of the if statement that you might have seen in the previous pieces of code. Now, what it does is you give it an element here, like a name, right? And you say, I expect the value of that name to be equal to the string Hayden. And that's what it will do. And it will basically crash or throw an error if it doesn't be equal to that. So now we're going to go and do that ourselves. What I'm going to do is I've got a file here called jestlib. It has my remove vowels function in it that is yet to be implemented, and I'm exporting that function here as well. I've then got another file here called jestlib_test, and what I've done is I've gone and written a bunch of tests in that file. Now, the important thing to notice here is I am importing remove vowels from jestlib. So I've got my implementation in one file here. It's not done yet. It's just called being stubbed. And that'll mean a lot to you after iteration 0, right? Because in iteration 0, you went and stubbed a bunch of code. So you've got a lot of code that looks like this, right? So you've got your implementation. It's currently stubbed. You export the code. You import it somewhere else. And what I'm doing here is I'm testing with that export. And I'm just simply saying, well, hey, I expect that if I remove vowels from AEI, I get an empty string. IOU, empty string. ANT, NT, old, old. Something wrong there, right? Think about that for a second. B gets me the letter B. High gets me the letter I. Cannot gets me CANT. Delicious gets me delicious with a funny little symbol there. It's also a little bit of an Easter egg. So we're going to go and test that now, which will be fun. First name in the chat has asked, are there any moderators in the chat? I'm not sure. I can be a moderator regardless. And Claudia said, watching from Angola, Africa. If that's the case, that's awesome. Technology. So I can go and write these jest tests. Now, as part of your iteration 1, you'll be writing jest tests like this, right? I'm not going to show you me writing them because, we don't want to spend forever on this, but, I've written them before. They come up like that. And then the next question becomes, well, how do we run them? And I run them by, well, I have to install jest into my, my folder, or in your case, your project, right? When I do npm install save dev for jest there, what will happen is that it will go and install it, right? You went through that with Yu Chao in the npm lecture. You can go and review npm if you're not too sure what that does. The save dev command, remember, it really has no impact on anything for you at this stage, but anytime that you install a library that is only really relevant for, how would you put it? It's only relevant for the development of things and not in production. And what I mean by that is, like, when we write tests, right? What will happen is that the developers care about that, right? But when we actually go and deploy that into the systems, it's not really tested as much, at least typically. So what I mean by that is, like, when something actually gets dumped onto, like, say, a Canvas server or a Google server, they're not often testing it in production. They've done all the testing before that point. Now, that kind of, like, distinction is not super, super critical. So if you don't really understand it yet, you can kind of sit on it for a little bit. I wouldn't worry too much. But now I've gone and installed Jest. The next step is to run it, right? So if I've got my little bit of test here, I can run this particular piece of code here, and it should work totally fine. Just a quick interlude. People have mentioned there's a fair bit of unrelated chat that's a bit distracting. All I'll say is that if good questions come up, I make sure I answer them on my voice. So for anyone who's not tuned into the chat or watching the recording, or they watching live but they just want to close the chat because they don't want to really read it, I make sure that anything that comes up there I address in the lecture itself. So you can regardless of how noisy someone is, I'll make sure that's covered. Now, if I want to go and run this, I do exactly what's there, and this is a really important line. I have to run this command here. Now, if you remember from the npm modules lecture, when you install stuff, it all gets installed to the node modules folder. If there are modules that are installed that have a particular executable, i.e. they're not just libraries, but they can run like programs, then they'll typically be in the .bin folder. And then for anything in that .bin folder, like Jest, there's Jest. So Jest is a program there, right? Now I've just tried to run it. Jest, without any extra parameters, will try and do a few things. But what I'm going to do instead is I'm actually going to give it a particular file to run here. And in that case, the particular file I want to give it is jestlib.test. So jestlib.test.js. So I give Jest a test file that I would like it to run, right? So when I hit enter on that, it will try and run that there. Now it is mad at me because I'm not sure. Let me have a look. Just failed to parse a file. We might be missing some code. Let's see. I haven't looked at the lecture code in terms of, there might have been, someone might have dropped something while copying it. Let me check if it's there. Actually, I don't think it'll be there. Let me go check what's on your, I think there's just a file missing. This file, I think, is the file I want. I'm not sure why it's not there. Just make sure it's definitely not there. Yeah. So this is included in your repo because if you don't have it, some things don't work. I think that should be it. That definitely needs to be there. Let's just check if that's the only issue. Replay. Let's go and run it again. Jestlib should work. Yep, so this one worked here. And you can see that I got a whole bunch of stuff here. It was like, 1 failed, 5 failed. Now that makes sense because let's look at the bloody file. It's not implemented. This is what I was saying earlier about your code can run correctly, but still the test can fail. Because there's a difference between your code just failing to run and it running successfully to tell you that everything went wrong. Which is like a funny little thought, right? Because at this point in your, illustrious career, you probably have a very one-dimensional view of that. Now we can see that everything failed here. It's saying that there was one set of tests, basically one test suite here. There were 5 tests within that, and 5 failed out of the 5 total. Okay, well, that's good. So this is what will happen in your project. You will go and you will stub your code, you'll write tests for it, you'll run it, or your tests will fail. But you're happy with your tests. So then what you do is, besides committing your code and stuff, you go back here and you go and implement the darn thing now. So I'm just going to go and copy and paste my code because we've already done it. Here, there you go. And now I'm going to go run my tests again because I've written my implementation. It's time to double check that they work using the tests that I've written. Okay, now in this case, what's happened? 2 have failed, 3 have passed. Tests failed successfully. I love that quote. Yeah, exactly. Now I can see here that what's happened is I've actually got errors in my test. Oh no. So someone asked that great question at the start of the lecture. What happens if people write tests wrong? Well, this happens, right? Is they actually might learn it during implementation. In general, it's something you should avoid. Clearly here, I've got an extra O, whoopsie, and I've got this extra character that I must have tapped, whoopsie. So I would go and, update that, run this again. Now it works. Great. So I passed on my test. Now I made this reference earlier about regression. And what I'm saying by that is like, if you went and say you were like, no, I want to rewrite my code. I don't really like it. So you simply go and say, string equals string dot replace all, a with nothing. Say you want to implement your function this way. Now I don't know why you would do this, but I'm just giving you an example. If you were to do that, also, new string here is, so here's a good example. Let's say I did that. Now, I was about to hit save on that before I noticed my bug. But you see, now that I do that, when I change my code for the same behavior, because I've cleaned it up, say, I run my tests again, suddenly all my tests fail. Oh, there you go. Well, not all of them, most of them. And that's so useful. That's so useful because now I'm like, oh my God, I had this like guardian angel here that I wrote in the past that has helped me understand what's wrong. And if I had a look, I would identify that that was the error. I'd run my tests again and I go, oh, thank God I had that because now I can clean up my code confidently, knowing that it's all going to go okay. So that's Jest in a nutshell. Like the cool thing about Jest is structurally it's really simple. It's like this format, it's this format here in the lecture code. We have more in we have more in the lecture slides as well. This is straight. This is taken straight from it. Obviously, the lecture slide code has the errors in it that I was trying to demonstrate, so keep an eye out for that. Pretty easy. And, we can run that totally fine. The next thing, though, which is fun, is that if we just run Jest without the extra variables, what it will do is it will go and run all of the files that it sees in that folder that has a .test.js on it. So that's a really useful thing. In fact, I'm pretty sure it just does it in all subsequent folders. So in the folder 2.3, it looks everywhere in the code base and looks for everything with .test and it will just run it. So I can just run that Jest part there. However, if I want to simplify my life more, what I can do is I can go and add a line to my scripts here where I don't need the source part, where I can simply say, hey, if someone runs npm run test, I want you to just run the Jest command. Now, you don't need to write it out like this. You could. This would work perfectly fine. And just for simplicity, I'll show you this one. So I say in my scripts, if I run test, it should execute that command. That's the command I have on the terminal, npm run test. It'll go and run it for me. However, the script stuff, it actually, if this makes sense, if you just give it a word, the way that like these Unix systems work is they kind of go like Jest. Okay, I have no idea what the hell Jest is. So then they go look through a series of predefined areas for it. And one of those predefined areas is this folder. So even if I don't have that, it will still work because it's going to go and look for jest commands left, right, and center, and one of those places will be that spot. So that doesn't really have much of an impact. It just simplifies your code there finitely for you. Cool. So the general structure of tests is that the outermost one, like there's no real rule and thumb. Like this outer describe will typically be like trying to describe what all of the series of tests are like, and then what you put inside the test string here will describe what am I actually testing. And you can also wrap these things in as many describes as you'd like. You wouldn't really do this for tests this small, but you could easily wrap that in yet another describe. No issues there at all. It's all just a textual structure, right? Like it doesn't, the words here don't mean anything. Like you could replace all of this with just like, literally emojis. That would be not problematic at all. It's just that when see how nice this is here with the outputs. It's saying, yep, remove vowels. Here's the test that it passed. Someone says, is each describe one test suite? That's a great idea. I always have a love for if we don't know something, let's try it out. So what I'm going to do is I'm just going to go and break this up really quickly. I'll take 2 tests and 3 tests. I'll paste this here. I'll call this one remove vowels 2. I will go and run it again. See what it gives me. Still one test suite. So it's treating the test suite basically as a file, right? That's the answer to that question. But now I've got 2 sets of describes and I can break that up. So again, the whole point is that all of the text stuff and describes and tests are just artificial structure. Now they're important so that you and everyone else understands what's going on, of course, but there's no real sense of getting it wrong except if people are confused. So it's a very human thing. You need to make sure it works because other humans need to understand it. Yeah, there's more general structure. This is a great piece of code to copy and paste if you're starting writing tests for iteration 1 because it just gives you a really basic example. No issues there at all. Note, the Jest syntax relies on some ideas around function syntax and function callbacks that won't be covered for another week or 2. That's fine. To use Jest in 1531, we've had to add a set a few environment attributes. This means you should only be able to get Jest working in week 3 labs or iteration 1 onwards. Yes. So what I mean by that is that I think when the lecture code was copied for this term, this file was probably missed. This happens when this hidden files can easily get missed. But the point is these things here, like this file and how the package.json is set up, which is specifically this line here, those 2 things are critical for Jest to work properly based on the code that we've given you in the course. So what that means is just from your perspective, this will only work generally in the week 3 labs. So if you want to go back to your week 1 or week 2 labs and test something, you probably need to modify it slightly. But again, that's more just a disclaimer. Most of you won't ever go near that. So that's no problem at all. Cool. Okay. So a few more concepts. How much we got left? Yeah, not long. Design by contract. This is something we kind of glossed over at the start because we figured, a little bit too academic for a while here. So let's get back to it. When we're testing or implementing a function, we'll typically be working with information that tells us the constraint placed on at least the inputs. So what I said to you earlier was that typically everyone has to agree on what a function does before they test it or implement it. This process generally is what we call design by contract. Contract is like an agreement. Design is like how we approach things. So we have to agree on stuff at the start. You kind of get that already. However, what I didn't really touch on is that typically there'll be an agreement about the bounds of things, because there was some great answers earlier about what happens if I pass in a non-number or a non-string or null or something. And usually teams of people will kind of agree on like, what are the limits of these things? So for instance, in this case, they might say like, oh, well, this function returns a new string with vowels removed. The input is a non-empty string and the return type is another string. Now you might be like, well, what's the point of that? What if someone passes in something else? No, I could pass in a number. And the answer is because typically functions are used in the context of bigger systems. And what I mean by that is if someone is calling the remove vowel function, the person calling it might be calling it in a place where the numbers they're passing in have already been checked and filtered by another function, And you might be thinking, well, sure, I get that. Okay, that makes sense. There's a function and it's like, we kind of know that the inputs are going to be checked a certain amount, so we can document that so that someone knows that it's going to be expecting something. Then you think, yeah, but what if someone just like abuses it? What if someone just like totally just ignores that? And it's like, well, that happens too, but that's why we pay developers and engineers and coders good money, because we expect them to read the documentation and be like, yeah, input is a non-empty string type and to behave like that. Now, again, we're getting into philosophies here, because there'll be certain types of industries and systems where even if you document what it expects to take in, you will still code in some checks that are like, what if someone just ignores it? And they're typically high critical systems and stuff, where if something goes wrong, someone might die or something might explode. If you're building a little like app like Duolingo or something, okay, what if a bad engineer ignores some code? What's going to happen? The website goes buggy, So again, I'm not saying that would be okay, but it's like important to understand the scale of what we're talking about affects how we'd approach stuff. Behavior. This is a really important note as well. So when it comes to software behavior, we don't talk about it a lot as far as I've seen in first year, but behavior is a really important word, and we use it to just describe what does the software do. So someone might say, what does it do? But like what you're really asking is like, what's the behavior of the software? So when we test software, we're essentially testing the behavior of the system, right? Because behavior, if you think about it, is just how people respond to, stimulus, I guess you would say. And software is kind of the same. You poke it, it does something. You poke it, it does something, like that. However, it's not possible to understand the behavior of every possible scenario, right? And that just is because sometimes it's just not feasible, because there could be a million different things. And the other time is that the implementation details are not critical to kind of the spec, or, it's just like not intended to be used that way. So there's actually a good example of some of these in C. And the reason I mention it is because there's this concept called undefined behavior. Undefined behavior is where behavior is not defined at all, often because the use case is beyond reasonable scope of expectation. So what that means is there is code out there where I think a good example is in C, right? Like in C, if you say like int main, and then you say int I, and then you say printf, yep, that was right. Printf I like this. I'm 90% sure, but I'm pretty sure that if you kind of go read through the C book and you're like, what happens here, right? Because I is not a value. I haven't assigned it anything. I think it's undefined behavior. And what that means is the people who wrote C, they didn't like want to build in all these different specifications and systems and be like, this is exactly what happens in this case. They were just like, it's kind of not really how it's meant to be used, or like, so like, we don't know what's going to happen is the short answer. I mean, you kind of could guess, but it's not clearly defined. The answer is it'll just use whatever's at that memory address on the stack previously. It could be 0, it could be something funky. So that's what undefined behavior is in a nutshell. And the reason we point that out is because occasionally when it comes to a big project like the one in this course, there'll be questions people might have like, what happens if X, Y, Z, or like, a good one we get often in iteration 2 is like, what happens if the server shuts down halfway through something? And we're like, we don't know, like anything could happen. And typically anytime you might hear about undefined behavior in labs or the project, it's usually reflective of the fact that we don't test it either. Because if it was defined, we'd be testing it. Oh, this is just a quick note. This isn't really related to the course, but whilst we're talking about behavior, this is kind of important. Another idea is called implementation defined behavior. It's usually when the people who set a standard don't really care about how someone does something. They just are like, well, as long as the box is a certain size and a certain color, we don't really care about what exact shade of red it is, And I think I don't want to go too deep into this because it'll take up time, but quite often people set standards and then people implement standards. Really good example might be like, the government during elections. There was a state election recently, council election, in New South Wales. And, the AEC they might have rules about, you know, you need to have this many boxes and this many stalls, and it needs to be open from 9 till 5 and blah, 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 right? Like they've got all their rules, their spec. But then someone might ask a question and say, hey, where does the AEC think we need to put the bin? You know, the bin where people throw stuff out. And the AEC, not that this conversation actually takes place, but they might just be like, that's not part of our set. They might say, that's an implementation defined behavior. They wouldn't, but they might be like, up to you, right? They're like, up to you. There are 1,000 people like you implementing the standards. That's a really detail specific thing. So it's like, it's kind of up to you because it doesn't really matter. They're like, it's not part of the behavior they expect. Therefore, it's not something they'd ever test or check. Therefore, they're like, it doesn't really matter. So kind of do what you want there. And the same thing happens in software a lot, is that there might be like a spec, right, that someone has to implement. Because think about it, there's one spec for the project, but there's 200 groups. Okay, so in all those 200 groups, there might occasionally be some aspect, not so much early on in the project, but later on, where like someone might interpret something slightly differently that isn't to do with the spec, and they might just be like a tutor, or someone might just be like, it's kind of up to you. Implementation specific behavior, because you're the implementation. So good example here is like where the text inputs are ASCII or UTF-8 encoded. So ASCII is like the old school type of text, you know, all the alphabet numbers and stuff. And UTF-8 includes like all the new emojis and things like that, blah, blah, blah. So, you know, if you ask that for a tutor, they'd be like, that's kind of implementation specific. We don't really care because we're not testing and it's not part of what we're trying to do. So that's a cool little fun fact. This is a cool little snippet right at the end here that just kind of shows the differences between testing. ByteByteGo does a bunch of cool stuff. This is just kind of taken straight from them, but they're kind of just showing, you know, and I love this diagram because maybe I can make it slightly bigger. I love this diagram because it kind of shows you that, like, I never talked about load testing here, you know, but that's like a real thing these days in big systems. It's like testing won't just be like writing code to check if the code works. It'll be actually writing code to check if the code that does work can withstand large volumes of stuff, right? Like, for instance, Netflix would be doing a lot of load testing as part of their dynamic verification, because they'd be like, we have 100 million users. I don't know how many users they have. We have 100 million users, and we know that when we release this new TV show, that statistically the worst case scenario is that 30 million of them might try and watch it at the same time. So they might go and test their code and their systems more broadly by like just trying to make 30 million requests at the same time and see what happens, you know? So testing is a big, big concept, and it's always evolving, right? Like load testing wasn't as big a topic for graduates 20 so years ago, because like, you know, back when we used to sell software on CDs, there was no notion of load, you know? Like if, you know, you play a video game, they don't need to load test a video game, but Duolingo needs to load test it, because what if everyone on the planet wants to learn Spanish at the same time, you know? So these things evolve, which is why I think it's so important that you get the gist of it, and I don't leave you with, here's the 4 types of testing that exist. So, you know, that's good. Anyway, that's it. Cool. Let's take a quick break, and then we'll get stuck into the next part. So we'll just do like 3 or 4 minutes. We don't really need to take breaks with live streams as much. So, yeah, cool. Chat in a sec.